So,
They also need.
So I don't think Alex is here.
hello.
So maybe they're using Maybe they're using everyday math. Is that not how? I don't know. Anyway, did you learn anything? Like, did you discover any theorems as a result?
I couldn't come to any logical conclusion besides amazement.
They still have them.
The only lobster show.
That's a good one.
I don't know. I might go to
So Jasper, it's really focused just on you. We'll never be able to see anyone else. So if you take this thing, yeah.
I wanted it that way, Mr. Scraggs.
I know.
so-
Well, duh.
Say hi. But no recognition.
How are
Jasper, right after this, in seminar
You
room.
bet. Okay, this is not working.
Scoot over, sorry.
you just don't know how to use it. It's like the plus minus thing is what you want to use.
Yeah, I'm pressing that. It's not working.
Uh-oh. Uh-oh.
Want to try?
Charles, how are you today? I'm okay.
I don't know.
I got to yell at Theodore Pettis today, which was like the best moment of my teaching career.
He's never had an aggressive. No, the best moment was the first time you called Charles Charles.
This thing.
What?
What do you think happens if I hit that?
I just try it.
I haven't even
Yeah.
done that in a while.
What?
I love
I can't
that.
even see you.
You see that?
Where is Julius? I can barely see him. It's like I can see his
I
head.
think the remote is
Jasper,
working.
we really don't need
maybe we
you
need to turn it
see
on.
your pants instead of your face.
So
I know
if you
you're
use
just trying
this too, you can make it go up and down. The round thing,
It's a little too complex.
obviously.
This is why boys are dense.
Now, actually, Jasper should be wearing Eric's shoes,
No,
and
that-
Eric should be
that's
wearing
true.
Jasper's shoes.
Yeah, that would be.
Oh,
That'd be a lot.
That'd be
That'd be a lot.
Okay,
Would
this
be
is
a
really not
lot.
working.
That's a lot, as Julius would like to say.
Hi, Julius. I literally did say
So
it.
extra. Julius?
Yeah, Julius, can you define extra for me?
No.
So wait, help me out. Give me an example of someone saying something extra.
So if Charles is like, isn't this the fourth partial derivative of the thing that Euler proved, what blah, 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 then Julius would be like, that's so extra.
Yeah.
So
kind
wait,
of, but,
it's
like, that's not a
interesting?
perfect
Is that what you're saying?
No. Like
the anti-intellectual Julius.
I know.
No, that's not how it's used.
Is that what we're talking about?
Mr. Spaggis, I've got an example. I've got an
necessary
example.
statement or like outfit or call for attention.
Say someone.
I've got one. So last year, every day when Alex, okay,
Go ahead.
Why am I screaming? Last year, every day when Alex would sprint to the front of the classroom and try to knock people out of their way so she could sit in the front.
Oh, that's so true.
It's true.
Okay. Oh, there we go. I got it working.
Oh, there you go. It just took half an hour. Now make it go back.
No, turn it.
No, there we go. That's good. There we go.
Wait, no, just do it.
Hello
That way, that
there. Raheem, where are your compatriots? There's Akshay. And where's Samya?
Where's everyone else in our room?
Samuel.
Oh, Alex is SDLC.
Okay, are you ready for this? Are you ready for
Both
this,
of
guys?
them.
Samuel is on a required
Got it.
field trip for computer science. What? What kind of a field trip do you go
You should
on
have
for
brought his
computer science? But seriously, what do you go do? Let's go watch programmers.
Just us.
Making us comfy.
I have a question about
Jackson.
this.
Yes. Oh yes. Isn't that? It can't just be. It can't be random, can it?
What did that person use to take the picture?
Someone else was with them.
That's
A
so
friend.
cool.
A friend
That
was
is
with
Oh,
them.
I can't believe
literally
this is like a bastard computer class.
Wait, it's did you?
No.
No, be on your computer class.
It's impossible for me to believe that was accidental.
I believe.
Do you really? Raheem, Akshay, how are you? Where? What? I know. What's going on with you? Oh, there's Samya. I was all worried about you, Samya.
Oh, true.
I was about to flip out.
And when he flips out, it's not pretty.
It is not. It is not. It is bad. Like I flipped out on Theater Pedestal. Alex.
Wait, why? Was he late to class?
No, it's even better.
Alex probably was at home.
No.
Yeah.
Alex, you're not at school today.
Wow.
Oh, she's here?
No.
Oh.
Oh my gosh,
Julius,
Alex!
that's so
I'm sorry to
scary.
hear that. This picture does fascinate me because it just couldn't have happened accidentally.
It was an accident.
It just couldn't have happened accidentally. Okay, here's your first problem to start with today, just to get us all settled down in the mood for math.
Sketch the domain.
I know.
Settle me down.
What should my name be?
Oh, okay.
Isabel.
Beach garden.
Look at all my look. Ah.
Oh, 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 oh. Are you downstairs?
I like his singing.
I don't. Oh, are we not muted? No, it's fine.
Don't do it. I want to listen to his humming.
My computer plays.
Let me see this pages for the problem set I started. Stupid thing.
I give up.
You gave up pretty easily.
No, I'm not on the computer. Not on the. Oh, there it goes.
It takes a while.
I think I have the 15-inch one.
Yeah, we have. Oh, and we both
Logan,
got
has a
math
question or an
screens 'cause
answer?
we're smart children.
As soon as you can ask for us to do it, I was going to volunteer.
Okay, excellent.
You ready? Or,
No, I'm
Okay.
not,
sorry.
because I don't sense that everyone is ready. I'm actually going to show the answer,
Oh,
which will. You can have the satisfaction of seeing if your answer is correct.
sounds good.
Wait, should we not raise our hand when we're done?
No, because I'm going to show you a response to this, a written response. There's a couple of those today, so someone is writing me. Oh. Okay, I'm going to show you a response to this, just so that you can compare your answers. Make sure that your answers agree.
What's the best way to show which side of a graph you mean when you're sketching a domain? Instead of shading the whole.
You just.
I think I would probably not. I probably would have written an inequality or in words like the thing. This is a solution from a text somewhere. The domain is a set of all points that lie outside the disk centered at the origin. So I mean that works for me.
They have it. Well, they have it in the set notation there.
Yeah, they do. So that's I don't personally love set notation. Set notation is interesting. So set notation became a big deal in America after Sputnik, and there was a big emphasis on making math more formal in the schools, and so that's when that really entered the American curriculum in a big way, and it kind of went away. And so if you like it, I encourage you to use it. It's very formal.
I use it in a couple of my problem sets.
Yeah, you do. I notice that you do, but it's not something I like using the brackets and saying X, Y, and the colon, like that sort of thing. That's set notation.
Just brackets. I was always taught that you had to use epsilon. Like in middle school, I would always you'd always have to say like X.
What
like
fancy middle school did he go to?
Sidwell.
There. Whoa.
What's epsilon?
Is he talking about X like in the set of?
Like this
X
thing.
like a member of
Yes.
set.
Yes. So that means member is a member of. X is a member of. So it's I don't know if it's actually. I mean, I wouldn't want to say that a Sidwell teacher wouldn't know what they were talking about, but I'm not sure it's an epsilon. But it may be.
Okay.
There's probably a different name for it, but I don't know. Okay, are there any questions about this?
I have a question.
Yeah, Logan has a question.
When I took the partial derivative with respect to x, I didn't write it f sub z.
High.
Actually, I think it's interesting that they say that. I think that is f sub x. It just is hard to read.
Oh, okay.
I'm pretty sure it is f sub x, because if it says f sub z, that's wrong.
Okay.
I think it's f sub x.
Did you write down your
Just difficult to read.
Yeah.
The original function is.
Okay. Hello, everybody. Let's do it. Now, this one, I do want you to let me know when you've discovered the answer to this, and let's compare our answers.
The argument log has to be greater than 30.
Oh, I do remember that.
need to be greater than or equal to y squared minus 16? No.
Just greater than, and it's minus y squared plus 16.
Oh no.
Samya, give us an answer.
I got 12xy.
That's what I got too.
Yay!
Virtual high five. Virtual high five. She's leaving me hanging. Okay, there we go. Okay. We'll fist bump later. I hate fist bumping.
Ready?
I'm not doing it.
Better at like containing the spread of
Potato,
Ebola.
potato.
It's supposed to be better at containing the spread of Ebola. Great. Thank you, Charles.
So if you're
for your
shaking
creepy
That was
information.
extra. That was extra.
If you're shaking hands, you're literally endangering humanity, Mr. Simons.
Okay. I'm okay with that. How did you do that, Samya? How do you know what order in which to do it?
You do them in order like that's written. So you do X and then you do X and then you do.
You know, I was interested to try to see if you did them in if you did f sub yxx, if you would get the same answer, and you almost the same answer, but not quite. And so I may have made an error in my.
F sub xy equals f sub yx.
That's true, but it's not. I don't think it's true that f sub xxy equals f sub xyx and f. I mean, you know what I'm saying? There are six permutations of that. Okay, I don't know though. Maybe I made an error. It's an interesting question. Okay, now we're going to play a little game in français.
Really?
Okay, you must répondre oui ou non. Okay, you cannot say. You must either say oui ou non. Okay.
Why isn't it? Ooh.
Why is he so pedantic? Raheem, oui ou non?
Oui.
What'd you say?
What?
Well, is your answer oui or no for this slide?
No.
No. Pourquoi?
Parce que il y a un X.
We make
Raheem, virtual fist bump. Bump. Okay. Yes.
Est-ce que le symbole n'est pas la même?
No, it's not, because it would. Well, that's an interesting question. So it's telling you, what to take the derivative with respect of. So
But
this
if
thing
you
here is
see,
saying
like a
it's-
random crazy function, you can say ddx of. and
no,
it's to
you
take
can't
the
with a
derivative.
partial derivative, because it's telling you the derivative that you're taking it with respect of.
I just
So-
mean, how do you know it's? Or else it would have said ddy. You mean?
Yeah.
Okay.
Okay. Oui ou non? Okay, there should not be a line through that. So that is the second derivative of x square root of xy equals 1 over root xy. Charles, oui ou non?
Is you say or in French?
Ooh, yeah.
I'm bad with notation. Is this the same as fxy?
I don't know.
Or is it?
It's part of the. That is part of the question. Rahim, j'aime bien votre français. Charles.
I'm inclined to say no.
He says he's inclined to say non. Pourquoi?
Because I know when you take the derivative of the square root of something, you get out a 1/2 multiplied by it, and I don't see that anywhere.
That is a terrible reason.
So when you do it, you end up needing to use the product rule, and there's a
Okay, so now Isabel asked a really interesting question, Charles. Explain the notation.
So the notation is taking the partial derivative with respect to x of the partial derivative with respect to y of the square root of x times x.
Okay, so which do you do first?
You take the partial derivative with respect to y.
Okay, and then you take the derivative. So what would it look like in
So-
terms of f notation?
F of yx.
F sub yx. Do you agree with that, Jasper?
I have no idea. I was really puzzled by that as well.
Mon Dieu!
so-
Mon Dieu!
What was the question?
Well, because
Notation is the same as F.
What does the notation mean? Which do you do first, the y or the x?
well, I mean, in this instance, it doesn't matter necessarily because f
That's
x
right,
y
it doesn't
equals
matter.
y x, but
That is
but
true.
I mean I would think you do x first, but that's just me because of the way you do f x y. It's the first one that comes first.
Well, the
But-
good thing is that it doesn't matter because of what was that person's? Oh my goodness! It was a Frenchman who came up with this theory. And what was his name, Max?
I don't see.
Oh gosh, Max.
No.
Fail.
Come on.
Clairaut's theorem. Clairaut's
He
theorem.
put a negative.
I know, 25 by Max's name. The Clairaut's theorem, so it doesn't matter. I believe it means take the derivative of y first and then take the derivative of x because of where this notation comes from. It's from that Leibniz notation. So Isabel, do you have a question or no?
Oh no! Now
Okay.
I'm good.
Okay. Encore. If f has continuous partial derivatives of all orders, then f sub xxy equals f sub yxx. Eric!
Je dirais oui.
You think we? Okay, so let's look back at our last thing because this was what I was trying to do myself. So let's find f sub yxx of this. So what would f sub y be, Julius?
12y to the third plus.
Wait. Probably. What happened to the x?
Oh yeah, 12y to the third plus times x.
Okay, plus.
2x to the third y.
Okay, I agree with you. Jack, what would f sub yx be?
F sub yx would be f sub y would be 3x or 12x y cubed plus.
So just take the derivative of Julius's with respect to x. So.
Wait, can Julius repeat his again?
So yeah, I guess
12x y to the third plus 2x to the third times y. They're the same thing.
Okay, so
then the partial derivative for that would be 36 xy squared.
So with respect to x, so
that would be just 12y cubed. Plus 6x squared y.
Okay, thank you. And Alex Powell, can you speak now? Yes? We can't hear you.
Hello.
Hello. What would the derivative of that with respect to x be?
Then it would be 12xy. So it would be same as.
Yeah, so it is the same. It's interesting. So it actually is an interesting question for me is if all of those partials are the same, if all of those third partials are the same, so, x, y, x, 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 y, x, I guess there are only three, aren't there? I don't know. Anyway, if all the third partials are the same, okay? So that's something I don't actually know, and there probably is a theorem about it, but it'd be interesting to try out and see. Okay. Oh, mon Dieu. We've talked about that one, and that one. And we are done with the oui or no. I asked you to think more about this problem, which confused everybody on Monday, okay? So, Raheem, can you read the problem again just to remind us of it?
Sure. The temperature T at a location in the northern hemisphere depends on the longitude x, latitude y, and time t. So we can write T equals f of x, y, z. Let's measure time in hours from the beginning of January.
Okay, the first thing says, what are the meanings of the partial derivatives? And just so that we remember, what would del t del x be, Charles?
Sorry, my
That's okay. Isabel, can you tell me what del t del x would be?
There we go.
Like a function?
No, what does it mean?
Sorry. Oh, it's the change in temperature as longitude changes.
Right, as longitude changes. Okay, Jasper, what's del t del y?
The change in temperature as latitude changes.
Okay, Logan, what's del t del t?
The change of temperature as time changes. Can I have a question?
Yes, you have a question.
How does this work given that the globe is not a flat, planar surface?
How does what work?
The fact that it's with respect to that the function is dependent on x and y.
Well, because the x and y are actually coordinates. I forget. I didn't teach these students pre-calculus, and had I, we would have done a ton of problems about global, because that's something I do, is spherical geometry. So in that system, x, y is actually telling you where you're, where you are on the globe.
So it's not like necessarily Cartesian.
Yeah.
Okay.
So like if I say Washington, I think we're at 47 degrees latitude and something, I can't remember what it is, longitude, but that is a ordered pair that basically defines me. How do your phones do GPSs, by the way?
No.
3 satellites, right?
I don't know. No. I'm saying, where is it on your phone? Do you just look at the compass or what?
Look at them. Oh, like to get the longitude and latitude?
Yeah.
Compass might tell you.
Google, I don't know. But anyway, so I was reading something that... Okay, well, I don't know what it is. No. There's actually a compass on this smartphone. What did you say?
Google Earth.
I don't know. I'm just wondering if I needed to know my coordinates at any time, which maybe I do, How do I find them? I know your smartphones can allegedly do that. But anyway, okay, Honolulu has this longitude, latitude, and certain such stuff. Suppose that at 9 a.m. on January 1st, the wind is blowing hot air to the northeast. So the air to the west and south is warm, and the air to the north and east is cool. So this is what we had problems with. Would you expect F sub x of that number? And okay, so let's start with that one. Okay, Isabel, you have an idea or a question?
Okay, so Honolulu is in the northwest, right? Because it's 20 degrees north and 150 degrees west, right? That's fair.
Well, no, it's at a point, 158, 21, 9.
So then my question is,
what does F sub x mean?
Well, my question is, how is the wind blowing relative in Honolulu? Like, is it blowing over that point from the southwest to the northeast? Like, I don't.
Yeah, I think it's blowing like this. So, like, here's the point of Honolulu.
So then, as you would go.
So what does F sub x of 158, 21, 9 mean, Isabel?
So it means how is temperature changing as longitude changes instantaneously at that point.
Right, so as longitude does what? As longitude
goes to the east.
No, as longitude increases. So which way is longitude going to increase?
Oh, I don't know.
Oh, okay, so yeah, tisk. Longitude 0 is in Britain somewhere, and it increases this way around the Earth.
It increases that way. It's negative that way.
No, it goes from... But 158, so is it going...
I think Honolulu is at negative 158.
Well, is it going in greater longitude or less longitude is the question.
If it goes to the right, I think... Oh, no. I know nothing.
Okay. Eric, help me out.
Then.
So... Wait, so latitude...
I am assuming, let me just say this. I am assuming that longitude increases to the west of Honolulu, that there is 159 degrees. That Honolulu, if it's here, there's 159 degree longitude here to the west of Honolulu.
Right, so away from the U.S.
Away from the United States.
Well, then you would expect it to you would expect it to increase because the temperature's increasing.
Because the air is warmer to the west, right?
Yeah, so the air is warmer to the west.
So you would expect that number to be positive, negative, or 0. What would you expect?
I would expect it to be positive.
I would too. But now that, assuming and I think I'm right in that the longitude increases to the west of Honolulu.
Yeah, no, you're right. You're right.
Yeah, I don't know. Okay. Okay, Julius, the second thing is F sub y. What does F sub y mean, Julius? It's how the air is increasing, or how the temperature is related.
Increasing with respect to latitude.
Yeah. Okay, so if you're getting higher latitude, as the latitude increases, does the air get warmer or colder?
The air is blowing to the northeast, so it's going to get warmer. Wait, air to the west.
Air to the north is cooler.
Well, the air to the north is cooler, but it's getting warmer.
Okay, so that's true. It is getting warmer, but if you're in Honolulu and you're moving north, what will you physically feel?
You will feel yourself getting cooler. But I think this was the question that I had before. It's like we're putting it's cooler in the north, but the wind is also blowing warmer north. So it's like depending on which one of those has more influence.
Right, but if I'm asking about instantaneous rate of change, think about stepping just as you walk north, you will literally feel cooler because the warm air is that way.
Right, so if you just freeze time.
Yeah, I mean, in an instant in time, if you are getting cooler, what would the sign of the derivative be, Julius?
Negative.
Yeah, it would be negative. So I think that is what's hard about it, is it's confusing but literally, like at that instant in time, all the air north of Honolulu is cooler than the air south of it.
But if the wind is irrelevant, then why is it in the problem?
I think it's trying to make you think about. I mean, I think it's giving you, information in an unusual way about where it's warmer and where it's cooler. That's all.
Okay.
It's not extra. as you say. Alex Powell, what about the last one? F sub c, F sub t. So that's talking about... Alex?
You're muted.
Oh, sorry. So I was saying that I think that's where the wind blowing comes into play for the dt. Del T, Del T. And so then I guess I would say that it is positive if the air is like blowing to the north.
Right.
I don't know. Yeah.
So like if you're at Honolulu, as the day progresses, won't it get warmer?
Right.
So as time goes on, because you do have this nice pleasant wind coming in, then I think you should get warmer. So I think that is also going to be positive. Okay, here we go. Akshay, I love this idea. Suppose I said, find that for that function. I mean, let's not do it, but can you tell me what I should do?
Start... take the third derivative in respect to z, then the second derivative in respect to y, and then the first derivative in respect to x.
Yeah, I mean, so I think that the order would be, z first, and you do that 3 times, and then y, and you do that twice, and then x, and you do that once. Jasper, yeah?
Well, so I mean, let's say that you wanted to take the partial derivative with respect to z, and then you want to take the partial derivative with respect to y, and then you want to take the partial derivative with respect to z again. Would you?
Right. I would not use this notation. But actually, here's the thing.
Do it?
Here's the thing, Jasper. I actually don't think it matters.
No matter what order.
I don't know. That's what I'm becoming convinced, and it's funny because I hadn't thought about this until this class. I mean, until this year. I don't think it matters. Okay. I think you can take any order of the partials. So, I mean, that's my theory right now. That's my working theory. But and my second answer to you is I wouldn't use this notation to do it, because if you wanted to take it in a specific order, then you know what?
Yeah.
This is not going to give you that information.
Got it.
Okay.
So you mean it doesn't matter for every third or for every second?
I don't think it matters in terms of any of the.
Like any number in time, as long as you.
Yeah, my guess is that the 6. If I do z 3 times, y 2 times, and then x, and 2z, and then I try it 2 times with z, 1 of x, 1 with whatever. I think I'll get the same answer. I think all the mixed partials must be the same.
And I think like if you wrote that out as a string of like d by dx and d by dy and d by dz, you could prove with Claro's theorem that any adjacent pair of derivatives is interchangeable. And with that, you're going to say that the entire...
Right. So it's like the way we prove the product rule when there are 3, things. We think of 2 of them as a product, and we use the product rule that we learned. So that's what you're suggesting. And so I think you're probably right. It's an interesting question. It's something I've never really thought of before.
What if derivative isn't continuous?
I'm saying that this derivative is continuous. So, I mean, I'm assuming this is a polynomial. Polynomials are pretty well behaved. So, okay, here's another fun activity. So I've got level curves. Oh, level curves. Remind me what level curves are, Samya. How do you get these things?
Are these the contouring lines?
Yeah, they are.
Oh,
so what are they?
Well, how close together they are represents like if the steepness. So if they're really close together, they're really steep, and if they're far apart.
Very good. Yeah, and so we're calculating that by holding z steady, right, and then like solving the equation for z at that point, and then creating the contour line. Okay, so here's some contour lines. And can we tell whether the partial derivatives are positive or negative at the point P? So Max, what about for f sub x?
So for f sub x, we're holding y constant and seeing how x changes.
Yeah.
And so if like to the left of P, it's
twice.
If to the left of V, it's going towards 8, and to the right of p it's going towards 4, and at p it's kind of like on level 6. So I'd say as x increases, it's going down.
Yeah.
And so it would probably be negative.
So f sub x would be negative. I'm pretty positive you're right, because as x increases, my z values decrease. Okay? So f sub y, Jack Schroeder.
F sub y.
How do we look at this?
Would that be? Can I phone a friend?
Yeah, you can. How about Akshay?
I think it's positive because as you go, as y increases, the lines are getting closer together, so you're kind of going up.
Yeah, and as I'm walking straight up, right, it's like if I were physically on this thing, I would be walking up a hill if I were going straight in the positive y direction. It wouldn't be a very steep hill, but I would still be walking up a hill. Okay, yes, do you have a question, or you want to try f sub xx? Okay, ooh, this is tough. Isabel, go for
Here
it.
we go. So as you go to the right, x decreases, but z decreases, but at a decreasing rate as you move along x. I would say that's positive.
Okay, so say that again. So she's saying, what do you think about that idea? So x is decreasing, the z values are decreasing as x increases, but they're decreasing more slowly. So she thinks that the f sub xx would be positive. Okay?
Yes.
Okay, good. And what about f sub xy? Charles, go for it.
So it's a little bit hard to tell from this graph, but it looks like the level curves that represent like 6, 4, and 2 are getting further apart as you move, as y increases.
I think they are.
So that means that z is decreasing at a decreasing rate, and it is decreasing more slowly as x increases.
So f sub xy would be
positive.
Positive.
Wait, can we?
So let's say that again.
So because the level curves are in the x direction, are getting farther apart in the x direction as y increases, that means that z is decreasing as x increases, z is decreasing at a decreasing rate, and the rate at which z is decreasing is increasing with y.
Because they're going like this.
Because they're going like that.
Yeah, they're kind of
in the x direction.
It's a little hard to tell, but it looks like at 10 and 8, see how they're kind of spreading, and at 8 and 6 they're further apart. But at 4 and 2, in 4 and 2 they're also, the distance between them is greater. That's a good thought problem because you don't know anything. Yeah.
So like the contour curve or the level curve for P looks like it's on the level curve 6, right?
It is.
And 6 looks linear to me.
Well, but we don't know.
Okay, well, can we say for a minute that is linear?
Okay.
No.
And the other ones don't look.
So what linear. How does that help you?
So I'm wondering whether that changes the partial derivative of x and y. Like, I'm not sure. What exactly graphically are we doing when we take the partial derivative of xy? Because, like, are we going in a diagonal direction?
Okay,
like
it's a great question. So what does it mean to say, what does physically it mean f sub xy? Is that what you're asking?
Yeah.
Okay, so Jasper, do you have thoughts or question?
Well, I have another question. Do you mind if I...
Yeah, sure.
Well, so I mean, one of the things, when we're taking the fxx, we're making the assumption that the function that between 6 and 4, because the contour lines are farther apart, that it's like that the rate is changing in a certain way. But I mean, my question is, how would we know that necessarily? Because the contour line, like for example, it could go from like 6 to 4.1 and then back up to 5.
Right, we don't. Right. We just are, this is what we know. So given this graph, I can't say anything with certainty without knowing what the function is. But do you agree that it's as x increases, the function z is decreasing but at a decreasing rate?
No, I agree. I was wondering, because it says like determined. It's more like an educated guess than it's like than a certainty, I guess. I don't
Alex Powell, I'm wondering if you have any thoughts about what f sub xy means geometrically.
I'm still a little confused about how f of xy is positive. Could someone explain that one more time? Sorry.
Okay, so Isabel's going to try.
Well, I think what it means is like, okay, as you go along x, is z positive or negative? And then because it's negative, and then it is negative, like it's decreasing. And then as you go along y, it's positive. Then because they're, wait, did you say it was it ended up being positive? No, it was then because like they're different signs, then it ends up being negative. Is that?
Okay, Charles is going to try again.
So I have something to think about as the geometric representation of f of xy. So f sub x is kind of like if you think of having a surface in 3 dimensions and you hold up like a meter stick that's only pointing parallel to the x-axis, so it's like parallel to the x-axis. The slope of that would be f of x, and then if you move that along the y direction and the slope of the meter stick changes, that's f of xy, the rate at which it changes.
Do you buy that, Alex?
Yeah, that makes sense.
Wait.
Yeah. So it's an interesting idea to think about. What's intuitive about it to me is the idea that, the value of the slope of the x, I think we can all get behind that idea. The question is as you're moving along the contour lines, won't it shift the way that thing changes?
Right.
Are you convinced or not?
Yeah, I'm convinced.
You are convinced. Okay. How about you, Logan? What do you think?
I like Charles's visual.
Okay. So what would you say f sub xy is?
I would also say it's positive because it makes me think of graphing derivatives. First derivative would be in the fourth quadrant, and then if you take that derivative, that would be positive. So that because it's approaching 0 plus the negative infinity.
Yeah. So Max.
So if this is the slope, right? So is that positive or is that positive?
Because this is a negative slope, and this is still a negative slope, but it's less negative, so the change is positive.
Okay.
What?
Yeah, so you're going from something that's like this. What he's claiming, okay?
-5
you're going from something like
1.
this at the axis, but as it moves forward, it's becoming less negative. So as it's moving up the y-axis,
and
it's becoming less negative.
And is that because the lines are getting closer together? How do you know it's getting less negative?
It's because they're getting farther apart.
Okay, so it becomes more gradual.
Yeah.
Okay.
Okay. Okay, we got to move on. But that's a great problem. I'm very pleased. Oh, here's one of the things that, and we're not actually going to do this right now because we don't have time to do it. One of the really fascinating things about these partial derivatives is there's a whole field of study called partial differential equations. And some of the most important partial differential equations in the world are things that we use every day. You just don't know that you use them. We use this thing called the heat conduction equation. The really famous one is the Laplace equation, which the Laplace equation looks like this. It's the sum of partial derivatives, and so there are certain functions that satisfy this equation, and there are really useful things that these equations do. So have you ever heard of the wave equation, stuff like that? All of those are typically Laplacian equations. And so when you go to college, you might take a course in partial differential equations, and it will be all these kinds of equations that are used in sound, audio, any kind of thing that involves a wave. All of that stuff is determined by a partial differential equation. Yeah.
Sounds really rough.
Can you take partial integrals?
Well, in fact, you can take what's called a multiple integral, and we'll be talking about that a lot in the rest of this course. So it's like you can take an integral with respect to x, and then an integral with respect to y. And so a multiple integral, actually, two integrals would find you the area of a plane surface.
So like when you use partial derivatives, you have to change the d to a del. Do you have to do like integral of something del x?
No, we use different notation for that. I mean, we use just regular notation. No, that's a lowercase del.
But
delta.
But like
so a delta
math
is
notation.
That, and then a del is that. That's a lowercase delta.
Yeah, but math notation, people use that for derivatives.
No, we use a hard d. So that's one of the things. This d looks different from this d. So I mean, I should write that for you. Like one of the things that's important is when you're writing these partial derivatives, right? There's a d that looks like this, which is we use in single variable calculus, but there's a d that looks like that we use in multivariable calculus. So make sure that you're using something that looks more like a backward 6 than something that looks like the letter D, because this thing here means it's a partial derivative. Okay, so you have to be a little careful when you're doing that. Anyway, these equations, there are zillions of them, and they're highly useful, and especially anything that involves waves. So I don't know, whatever you're interested in, electromagnetism, you name it, the wave equation is used all the time. Another kind of interesting use of this is in forensics. There's just if we could read this, Raheem, would you read this problem for? Because I love it.
Yeah. Crawling speed of larvae. Okay. In a study on the northern blowfly, the crawling speed of the larvae is it larvae or larvae?
I guess it's larvae.
Larvae.
Larvae, yeah.
Was found to be a function of body length and ambient temperature.
And there's the equation. So just read the text.
Okay, where v is the speed in centimeters per minute of the larvae, L is the length of the larvae, and T is the ambient temperature. Notice an increase in body length or an increase in temperature will increase the crawling speed. This result is very useful in forensic entomology, the study of arthropod biology to criminal matters, for estimating the time that elapsed following the larva's departure from the corpse.
So they can actually measure these animals, these organisms, and use their body length to determine time of death.
Wait, really?
Love that.
But what if they grow over the time that they're crawling?
Well, this deals with it.
Wait,
That's the whole thing.
Confused.
So it's like they can figure out if it's in a certain,
it's like a maggot.
They're moving forward.
Right,
yeah.
so
They're moving towards it?
No. They're going to live their life outside the body.
So they
hang up there long enough. Yes.
So then how does that tell you the time of death?
Well, because I don't. Heaven knows.
This is so weird.
Yeah, but anyway, notice though, these things here, DVDL. Now notice, I was just saying, look, don't use this notation, but you do see this notation in the real world. It's like when I talk to students about logs, I say natural. I always say logs, but I always mean natural log. And students are like, what log are you talking about? Well, in real math, we only really talk about natural logs. So this too, I mean, I understand that this is actually asking you for a partial derivative, although it's not clear. But I think they're partial derivatives. That's a big field of growth for, like, if you're thinking about being a mathematician, which all of you should be thinking about being. That is a big field of growth. Partial differential equations. Okay, so let's do a problem about mixed partials. Okay, consider the function. So we have a function f of x, y, z, and I want to just see if we can list all the possible second partial derivatives.
Just without the function, just.
So f sub x, y would be one, right?
Mm-hmm. I got it.
Okay.
And you can't repeat them.
Mm-hmm.
Probability.
Yeah, it is a probability. Eric, how many did you get?
I'm still doing it, but I think it looks like it's going to turn out to be 9.
9? Wow. Okay, tell me.
What? Sorry.
It's definitely 6.
Wait, can you switch the...
No, because that's the same thing.
Oh, sorry. Yeah, sorry. So... Wouldn't.
Is it?
Okay, so Julius, help him out. What do you think? Julius?
Which one's the same one?
What?
If you flip them?
If you flip them and they're the same.
Yeah.
Well, if they flip them,
then I'm only counting
then
them
it's
once.
six.
Yeah.
Yeah.
That's right.
So
that's right.
six. So six then.
Okay, can you
not
read me
counting
yours?
like notation wise?
F of XX, F of XY, F of XC, F of YY, F of YZ, F of ZZ.
Okay, so that's the 6. Now, and actually that is 3 factorial, right? So that makes sense. The permutations. I mean, do you remember permutations? Well, maybe not.
Yeah.
Okay, so let's see. Number 2. Here's our function: x squared y plus 2xz squared minus 3y squared z. Which ones are the same? So the same would be f sub what? Which two are the same, Jack?
F sub F sub what?
Well, so which ones the ones where so like f sub xy, I will give you one, will be the same as f sub yx. Okay?
Oh.
So can you give me another pair that is the same?
Yeah, F sub XZ and F sub ZX, I think.
That's correct. And there's one other one, which is what, Logan?
F of YZ and F of ZY.
Yeah, f of yz and f of zy. Okay, Samya, how many second partial derivatives do you think the last thing has?
4 factorial.
I didn't ask you. Yeah, well, he said it, so 24, I guess.
Do you think? So let's see if we can. So wait, 4 factorial is 24. Okay, I agree with you. Now so can we actually let's try to figure if we can figure out all 24. Okay.
All right, go.
So let's see if we can get this. So it's p. So let's see, p sub x.
This is awful.
Oh, it's not awful.
It's awful.
My goodness. I agree. And I think that anyone who thinks it's awful is lame. Hold it. I'm doing math.
Oh my god, I'm gonna die.
We'd be so sad.
Oh, wait.
Thanks, Iz. Her nickname is Izzy, and I shortened it to Iz.
You sound like Miss Sweeney.
I'll be on 16.
I know. I don't know that 24 is going to work.
No, it's 20.
What were you going to ask me?
I was going to say, is this like
How is she
10
done?
when you do
Second partial derivatives.
Is this like 4 choose?
Yeah,
I
something
was
like
doing.
that. It's not just a permutation. Yeah.
I was doing fourth partial.
Oh, no wonder. No wonder she thought I was awful. She's not just a whiner. So wait, Samya,
Yeah.
read me what you have.
Okay, WW, WX, WY, WZ, XX, XY, or XW, XZ, YY.
So wait, you've
YZ.
already gotten W. You've already gotten W, XW, because that's the same as WX.
He was right.
It's 10.
Oh,
I think it's-
so all the ones that equal each other, you don't want me to count?
Yeah, so I think it's 10.
Okay.
So wait, Raheem, go for it.
This one
What are
has
the
6 units.
Alright, WWWX, WY, WZ, XX, XY, XC, YY, YZ,
Oh,
DZ.
it's like
Yeah.
Oh, wait, no, it's 11
So
then.
that's a pretty shape, though, and that's an interesting thing. So now Max has an idea that it actually may be related
It's a
to.
function.
0.
What did you think it might be?
It's
Triangle numbers.
combinatorics.
Yeah, it's a probability question that I'm trying to get you to see if it's. So it's not just 4 factorial, right? It's 4 factorial, but it's something else is happening because you're multiply counting many of them.
Right, and then also like if you wanted to find the number of like third partial derivatives,
Yeah.
there would also be a different number.
Right. So there's a little challenge for you. Figure it out, Max. See if you can figure this out. Not right this moment, but it has to be figure outable, right?
Yeah.
Because there's a pattern that's happening.
Is it how many 3-element permutations of these 4 elements exist, or 2 elements?
Well, so that would be 4 choose 3, right? Is that what you're talking about? But I don't know for this. What is 4 choose 2? How do you calculate 4 choose 2? Do you remember?
And as you go from
NCR.
1 to 2 to 3.
Well, that's one thing. Okay, let us continue. There's this thing called the differential that I think you should know about, which is just like you remember from the days of, do you remember f prime of x? We used to write it as dy dx. And we can do the same in partial derivatives. There's this thing called the total differential. So I only want you to know about this, not because I think it's super important, but because it exists and some teacher in your life may one day think it's important. Now, can you explain why this is the total differential, Logan? I mean, what's going on here?
So it includes it includes 3-dimensional space. So I guess that's.
So what is this term doing where the arrow is?
So that's the change in z with respect to x.
So it's saying how is z changing with respect to x multiplied by this dx, and this term is dealing with the
change in z with respect to y.
Right. So if I had 4 variables, I would have 4 terms, and I would just have to deal with each term along. So that's sometimes you may hear that phrase, the total differential. It's easy enough to find. We don't need to do it. However, this I do want to spend some time on because it is a return of one of my all-time favorite topics, which is Taylor polynomials.
Oh.
So Taylor polynomials, you can use partial derivatives to find a Taylor polynomial of a multivariate function. Now, this is something unique to today in class, so for those like for Alex, Johnson, Samuel, and Coleman, we'll need to make sure they get this. So this is the expression for a Taylor polynomial, of degree 1. It would be a linear thing, okay? And it's linear in that x linear in x and linear in y. A quadratic polynomial is quadratic in x and quadratic in y. Notice that the quadratic polynomial at the bottom has to have this term right here, which is x times y. And notice that the coefficient is determined by the partial at, the point of interest, 0, 0 in this case, which is just, I think that's all that we're going to talk about. So this term here is going to tell us, the first point. This is going to tell us the y part. This is going to tell us the quadratic part in x. This is the product of x and y, and this is the product of y.
Oh, so you're just showing. Wait, why are they both first degree?
They're not. Sorry, this is a polynomial of degree 2. Sorry, it should say degree 2. It's a typo. And you know what else is missing from this one? What's missing from this one?
The initial term.
Yeah, f of 0, 0. So we need to add that.
Okay, wait, don't click away.
Like a curve
Plus.
that tries and fits in.
Sorry, I need to turn this off. I need to add plus. Yeah, f of 0, 0.
Why is it 0, 0?
I'm picking that.
Oh,
it's your point of interest. And I think I want to do 0, 0 most of the time because think about how hard these things would be if they were not 0, 0.
They're already really hard.
Yeah. So now, it's actually not super hard to remember in that your x term, the coefficient of the linear x term is just the partial with respect to x at the point. The coefficient of the y term is just the partial with respect to y at the point. The coefficient of the squared term is going to be the second f sub xx over 2, okay, et cetera, et cetera, et cetera. Yes, Logan.
I'm having trouble with the...
Wait, let me point out one thing here. Could someone explain why this one isn't over 2? Whoops. That was bad.
It's not squared.
No, but why don't I have to have it over 2? Max, what's the deal?
So, like, when you say you first want to take the partial derivative.
You better speak up because there's loud stuff happening.
If you first take the partial derivative with respect to x, then you'll get, or I guess would you be taking the integral?
Well, I'm just saying here.
Or derivative. So you'll cancel out an x, but then you do it with a y, and so you'll end up with it's like, because for xx or yy, you when you take the derivative of x squared, then you get 2x, and so the 2 cancels out with the other 2.
I think I'm asking a different question.
Okay.
So let me, I'm not trying, Charles, do you understand the question I'm asking? Can you read my mind better than Max could?
I think that f sub xy, 0 times xy, used to be 2 terms.
Yeah.
Whereas like f xy over 2 and f of yx over 2, but they just, because they're the same.
It was 2 terms. There were 2 terms that are like this and were combined because they're the same coefficient. Okay? So that's interesting.
But did x squared and y squared? No. Never mind.
Okay, let's look. I'd like you for class on Monday to find the linear and quadratic approximations, Taylor polynomial approximations for this lovely function, cosine of 2x plus y plus 3 sine of x plus y. Make sure you copy that down. And second, I want to remind you that you have some really easy stuff to turn in. It's theoretical, but it's not hard. It's a page of stuff that you should turn in tonight. That's from an article about wave and the possibility of using waves for generating power. Like, that makes really good sense to people, and I mean, that sounds like such a promising renewable energy resource. It turns out that it's very hard to harness that energy, but it's an attempt to. The article talks about the mathematics involved. Okay, so I will see you all on Monday, and please do this problem by then. Have a lovely day. Bye, bye, bye.
Au revoir.
Au revoir. Bonjour. Bonne journée.
Hopefully you really speak French with
Oui.
that accent.
I always speak French with that
Another
accent.
day off today.
Probably.
But it seems like he wasn't in school.
He wasn't at school.
I had another court date.
He was not the one with the court date. That was
No,
Coleman.
that was Coleman. Oh,
No, you were asking about Alex Powell.
No, it wasn't.
That XY term was the result of
I'm
taking the
gonna
derivative
text Coleman and be like,
product
you
rule.
go to court again.
Say again.
The f of xy term between the xx and yy. That was the result of taking.
So, like, there was one term that was fxy 0 times xy, but that over 2. But there was plus f sub yx at 0 xy over 2, and those are the same terms.
So you can group them.
Yeah.
But where did the original ones come from?